will people care about that? Will people buy it? You do have to think about what the commercial aspect is. So I think to some extent, battery companies you would think that they would be looking to incorporate pseudocapacitive materials into their product line, except really it breaks the mold of the consumer training that's been done. It used to be for battery companies that they wanted you, I mean, we all did it, you would buy a battery and it was a primary battery. You would throw it away, very unfortunately, because it has a lot of toxic materials in it. But you would throw away the batteries and buy a new one. When you buy a new one, where does your money go? To the battery company, okay? And I'm not saying that battery companies are evil. Now they're doing some, certainly they've always done some recycling, but they're doing rechargeable batteries. But even these don't last that long, right? I mean, you probably have all in your cell phone had to replace a battery at least once in your times. And so even rechargeable is not infinitely rechargeable, but with supercapacitors they could be. They could be. So just kind of wrapping up here, looking at hybrid supercapacitors, this is where you have two different kinds of electrodes. The way I think about this, and this is the asymmetric form, is that you would have maybe an oxide-coated carbon on one side that is pseudocapacitive, and then on the other side you just have a double layer carbon. And the reason you would do that is that you could actually spread out your voltage range a little bit by doing that. Okay? So if you are concerned about having, if as a designer of a device, an energy storage device, your principal aim was to widen the voltage window, that's what you would do. There's some downsides to that, but that's what you do. So you'd make an asymmetric supercapacitor with that. You could also do what I said before, which is to composite. You could have a battery electrode on one side and typically you'd have a double layer capacitor electrode on the other. For those of you looking for more understanding of what's happening in industry, these are the major players, mainly in the U.S., but also JM Energy in Japan is a big player in this. Maxwell is the one that people have heard about the most. Their products are shown here. They look a lot like batteries, right? They have these cylindrical packages, and they even have, for bigger things, they have blocks that look like battery blocks. Here's an example of a D-series device, 350 farads. That's big. That's a lot of charge to be able to store, right, in one thing. At 2.7 volts, which is pretty typical. Usually if it's a organic electrolyte, you'll see a voltage of about that. And then you could change the voltage of your actual power storage unit by stacking these, by stacking the capacitors. But you could see pretty good properties, power and energy, specific power. Ioxys is another one. They tend to use activated carbon with PC, that's propylene carbonate, and a little bit of hybrid stuff with lithium. And they do have an ultracapacitor, same thing, with acetonitrile, which is another one of those organic electrolytes. Maxwell had listed application areas. So this is what Maxwell thinks the applications areas are. Transportation, regenerative braking, right? That's one that's pretty obvious. If you had an opportunity to slow yourself down, right, and make energy at the same time, you would do it. Versus slowing yourself down and making heat and dust, right? Which is what you do when you use traditional brakes. Okay, so that's a big one. Capturing energy, again, these sort of intermittent power events, that's an important one for transportation. For utilities, so on the grid, for load leveling, a lot of times you'll have spikes in grid power, And so load leveling tends to damp those out, right? And so a lot of load leveling is especially needed for renewable power systems, because renewable power systems are much more intermittent than coal-fired power or nuclear power, right? Because when a cloud comes over my solar cell, suddenly its output changes, right? But it's very hard to imagine how the power output from a coal-fired boiler would suddenly do anything, right? It's a huge furnace with all of this heat that's already built up. It's not going to be fluctuating very much. So some R&D directions, I think, just to reiterate some of these. I'd start with new electrode materials, but right behind that, I'd be looking at these electrolytes, ionic liquids, right? And mixing electrodes and hybridizing structures. It's an extremely creative space right now. And so if you look at the research world, everybody can do this. I mean, it's kind of magical. So many people can actually make, leading edge types of progress, because really it's not all that complicated. It doesn't require extensive equipment to do this. So a little bit here and there, some circuit analyzer types of things. We'll talk about that, but not too much. And you can build these things in a laboratory. Again, be safe. If you're using toxic chemicals, use PPE, use a glove box. But it's not really that hard to do otherwise. So it's fun in that way. Here's a slide on ionic liquids. I think I'm just going to skip through this since we're out of time. But I would say here, looking at some of these ionic liquids in the last column, you can see that their voltage windows are very high, up to 6 volts. That's a huge advantage for them. And so just to close this out, I won't read the slide to you. The projected market looks like supercapacitors will be, 3.5, maybe more. I don't know if you saw the news out of Paris today, but a climate accord was reached with 196 countries. And they essentially said that starting in 2020, they were going to dramatically reduce the release of greenhouse gases. Okay, and that means that there's going to be a bigger emphasis on renewables, and so who knows what this market could become. The roadblocks are high price, and then there's really, people in industry haven't used capacitors that much for large-scale power things, and so just that unfamiliarity of that voltage decay during discharge, right? And how to design a circuit to manage that, right? That's a roadblock. But there's so many opportunities, certainly even more than are listed here. And I encourage you to use your imagination on what opportunities you want to create. So with that, I am done, and I thank you for your time, and I'll be happy to take questions. Any questions? Must be some. You were very attentive, I will say. I mean, when I was watching you, everyone was listening. So does that mean that you understood everything, or does it mean that this was the least technical talk you've heard, and so you can only talk about nerdy, geeky things? Is that it? I don't know.
Is there any specific reason this ruthenium oxide is best?
Yeah, it has to do with, and I think I have seen, sort of an explanation of it. But ruthenium oxide has this wonderful set of oxidation states that allow for this fast redox. And there's no comparable. I mean, manganese is close, and it's certainly much more affordable than ruthenium. But that's what it is. The ruthenium just has these wonderful oxidation states that make these fast redox reactions. Yeah. Yeah.
So you have mentioned that for the high power applications, supercapacitors are preferred.
Power.
But
Yeah.
as far as the mobile communication is concerned, we use batteries.
Correct.
Even in the MacBook and in iPhone, we use that pouch batteries. So can we replace those batteries in near future with these supercapacitors?
Yeah.
Low frequency applications.
So the question is whether we can replace batteries with supercapacitors in portable electronics. The answer is that the manufacturers and commercial entities compete on the basis of how long your battery lasts in your device. So how long your device, that's a combination of how much energy is in the device, is in your storage device, and how energy hungry your hardware is. But the point of it is they're not competing on power, except to some extent they're competing on recharging power, right? The speed to recharge it. So I think that's where there could be something. So I could imagine a near future in which you had a supercapacitor sitting with a battery in a portable device, and you said, you know, I can charge a third of my phone in a minute, 1 minute, right? 1 minute, so I can get through the rest of the day while I'm getting my coffee, right? Why wouldn't you say, well, if you could do that, why wouldn't you go all the way? And the answer is, it would be too heavy. It would be too heavy or too voluminous. It would be too large. But I could imagine a place where a company would say that 1 minute, 1/3 charging is valuable enough to my customers. I think I could sell that. I mean, I think I would buy it, frankly. I would buy something where if you told me, you know, this device, if you could get a third of your charge in 1 minute. I can't tell you how many times I've been sitting there and my phone was dying in power, and I'm thinking, oh, please, just a little bit more. Maybe that's my own problem, right? I'm addicted to my own email or something, and maybe it's, you know, somebody telling me to cool it on that. But still, it's frustrating. And so, again, this hybrid concept. And of course, it's a full spectrum possibilities. That's why I like to talk to young people about this. You could do any of these things, and to some extent, it's a hard. You know, there's lots of quantitative, hard answers to what you should do. But in other cases, it's very creative about how you would divide, you know, this kind of electrode with that because you want this attribute out of it. So it's very, very creative as well.
One more question. For renewable energy storage, can we replace batteries by pseudocapacitors?
So can you replace for renewable energy? You know, I think that there's some good opportunities there because you know, you have more tolerance for weight in renewable energies, like in solar power. You have more tolerance for heaviness, for wind and solar. I'm not saying that people don't like light things, but I think that this high cyclability is a huge advantage. So if your solar cell is going to last for 20 years, right, and you're going to have a cycle of storage every day, right, well, that's going to end up being, you know, what is it? How many cycles is that? 6,000 cycles, right? 6,000 cycles for 20 years, 6, 7, 8,000 cycles. You don't want to be halfway through that replacing your batteries. I think that there's a good case to be made for doing supercapacitors, and you know, they also want to make solar cells that last more than 20 years. Although I think even 20 years is pretty aggressive right now. But ideally, that's what they're saying they would do. Wind turbines, right? Same thing. You should be able to put a wind turbine up and let it just spin and spin and spin like the Dutch did for so many years, right? But wind turbines don't last completely that long either because they have intermittent speeds, which causes gear wear in the transmission, right? And so they have to be serviced. But you'd still like to be able to put an energy storage unit next to it and just forget about it for the lifetime of the wind turbine, as opposed to changing your batteries every so many years. Any other questions? All right, well, thank you. I appreciate your time, and we will see you tomorrow. Yeah?